Okay, YouTube, in my last video we introduced the concept of a polynomial function. As we go forward, our aim is going to be at making the graphs of polynomial functions, which we know to be these very smooth curves that are always continuous and have end behaviors that either rise or fall. And so in this video we're going to look at is the end behavior of a polynomial function, or the behavior of the y values as our x values go to the right and go to the left. And it comes down to one of four possibilities. We can go ahead and take a look at our table right here, but as we look at polynomial graphs here, it is either the case that your function is either going to rise or fall on the left-hand side or the right-hand side. So the four possibilities happen to be these. We could see that on the left side we could have a falling behavior, on the right side a rising behavior, or on the left side we could have a rising behavior, on the right side we could have a falling behavior. Whereas the other possibilities would be that we're both rising or we're both falling. Now, after admitting this fact, the question is, how could we gain some insight as to what the ends of our graph will be doing just by looking at the function itself? And there is actually a way we can determine this if we have our polynomial function written in standard form, which I guess it's not always true that you have to have it in standard form to identify these things, but with it written in standard form, it's very easy to identify the leading coefficient. And it's also very easy to identify the degree. We can get these two bits of information here. And the reason why that's important, I've got a little Desmos exploration up here, but we'd say, let's look at a really basic polynomial function. That would be f of x equals ax to the nth power. You'll notice that I have no other terms. This is just a monomial. But basically what I wanted to do was look at the effect of n, or the degree, upon the end behavior of the polynomial, as well as the effect upon the leading coefficient upon the end behavior of the polynomial. So right here, what I want you to see is this. Right now, our degree is 1. We have a first degree polynomial, and our leading coefficient is a positive 1 here. But our end behavior is such that the left side of this polynomial here is its y values, which is what we're looking at here. We're looking at what are the y values doing on the ends here as our x values go to the right and go to the left. And I notice that as our x values go to the left here, look at your y values. This graph is falling or decreasing as we go to the left. But as we go to the right, its graph is increasing here. So I would comment that the end behavior on the left and right hand sides of this graph are different. One is going downward, one is going upward. So let's look at what happens when our degree changes here. So we've got a first degree polynomial. If we change this to second degree, all of a sudden now on the left and the right our graph is rising, both sides. And then we say now third degree falls on the left, rises on the right. Fourth degree, rises, rises. Fifth degree, falls on the left, rises on the right. Then rises, rises for sixth degree. And what I'm noticing here is that it's kind of this playoff between falls left, rises right, and rises left, rises right. So what I notice is every time we have an even degree here, our end behavior on the left-hand side of the graph compared to the end behavior on the right side of the graph is the same. And every time we have an odd degree, like seventh degree here, our end behavior on the left is different from the end behavior on the right. So this is a crucial piece of information and essentially summarized here in our table. So I'm going to go back and look at this table. It says when our degree, looking at this here, it says as x increases or decreases without bound, that is as we go to the right and as we go to the left, the graph of the polynomial function here, so we're giving this polynomial function in standard form, but what we're really looking at is the leading coefficient in the degree. Looking at those two pieces of information, we could say that for n being even or odd, and n, remember, is the degree of this polynomial, the degree n. So if n is odd, what this essentially says right here in these two possibilities is that the end behaviors have to be opposites. They can't do the same thing on the left side as they do on the right. And whenever we had an even degree, even n, just like we just saw, the end behavior happens to be both the same on the left as it is on the right. Okay. So kind of going along with this investigation, let's look at when a is negative here. And what I want you to see is that the same thing holds true when n is even. We have second degree here, fourth degree, sixth degree, eighth degree. Whenever this is even, the degree is even, we still have same end behavior on the left as we do on the right. But what I want you to notice is that as I flip through all of these, one side of this graph, the left or the right, is consistent throughout the whole thing. And what I want you to see is that the right side of this graph, check out the right side here. As I go through all of these behaviors, the right side of the behavior of this graph is always falling. And the reason why is because we have a negative leading coefficient. Had we had a positive leading coefficient, let's put this back to positive 1. Same thing happens, even and odd with being the same and different on the left side, but we'd say look at the right side of this graph. The right side ends towards positive y values, or it rises. So what we could say is also with respect to our behavior of our graph, we say that the leading coefficient here, and we represent this with a sub n, Down here, this says if a sub n is positive, we're going to write this. We say LC is greater than 0. This is LC less than 0. Here we've got LC greater than 0, LC less than 0. But I want you to see that the leading coefficient being positive here directly influences the right side of the graph. And the leading coefficient being negative here directly influences the right side of the graph. And the same thing here, leading coefficient positive, right side ends up. Leading coefficient negative, right side ends down. So what I can say is this, that if our leading coefficient is positive, then the right side of our graph must rise. And if our leading coefficient is negative, the right side of our graph must fall. We can always narrow down the right side of the graph just by looking at the sign of the leading coefficient, and then narrow down or pin down the left side behavior just by knowing whether your degree is even and odd, and whether or not our degree would dictate that the end behaviors are on the same on the left and the right or different on the left and the right. Okay, so knowing this behavior, let's put this into practice here. And actually on this here, I got this little chart here. It says that your leading term is a sub n x to the n, where n is your degree, so n is odd. Okay, then we have opposite behaviors here. This is a down up orientation, where this is an up down orientation here. And if n is even, we have up up or down down. And then this over here on the left says if your leading coefficient LC is positive, then you have right behavior. Look at this, the right behavior ends up on both of those. But if your leading coefficient is negative, then the right hand side behavior ends down. So let's put this to use. It says using the leading coefficient test, determine the end behavior of this graph, x to the fourth minus 4x squared. And I'll tell you what, if we look at this here, we just say that our leading term, our leading coefficient, we'll just write this down, is equal to 1. I'm going to indicate that that's a positive value here. Positive. I'm also going to say that our degree here is equal to, it looks like a fourth degree polynomial. So we say fourth is a quartic. And so what we're going to say is this, even. And so knowing this, I would say that the key we're going to write here is starting with the right side behavior of this graph. I'm going to say because this is positive, this ends as rising on the right hand side. And because this is even, I know that the left hand side has to be the same behavior. So looking at checkpoint 2 here, it says use the leading coefficient test to determine the end behavior of this graph. Well, I'll tell you what we're going to need to do first is FOIL this back out, multiply this back out. So I'm going to leave this 2x cubed out front, and what we're going to do is we're going to multiply or FOIL what's in here first. So we have x times x is x squared, x times 5 is 5x's, negative 1 times x is negative x, and then we'd have negative 1 times a positive 5 would be a negative 5 here. So what we end up with is this expression 2x cubed times in parentheses x squared plus 4x minus 5. And then now we're going to distribute this 2x cubed throughout, and we get this. We get 2x to the fifth, so we must have a fifth degree polynomial, plus 8x to the fourth, minus 10x to the third. And so now looking at this, I'm going to write these out again. We say the leading coefficient is equal to 2, and our degree, we have a fifth degree thing. So what we're going to write here is that the degree is odd, and that this is a positive value. So we could say that in terms of behavior, we say that starting with the positivity of the leading coefficient, the right side rises, and then the left side must fall because we have to have opposite end behaviors on the left and right if our degree is odd. So this last little thing here, it says the polynomial function given by f of x here models the ratio of students to computers in U.S. public schools x years after 1980. So it says use end behavior to determine whether this function could be an appropriate model for computers in the classroom well into the 21st century, explaining our answer. So what I want to kind of do is indicate the fact that what they've told us is that x is, let's see, the number of years, so years after 1980. And so right here, this is 1980, right at the beginning. It is kind of like time equals 0 here. And so this is modeling our ratio of students to computers. So we'd say ratio, let's write this in, of students to computers. So what's happening to the number of students per computer, that ratio, from 1980? And so what I notice here is we're just going to use this, what we call the leading coefficient test, to explore end behavior. So our leading coefficient in this case is negative 0.27, and our degree in this case happens to be third. So we have an odd degree thing, and then we say that our leading coefficient is negative. So what we know about our end behavior is this: on the right side, it must fall. And don't worry about this comma here. It must fall on the right side because the leading coefficient is negative. And then we'd say our third degree polynomial would indicate that it had to start up on the left side. So we would have something that I don't know what it looks like in between. But we have it coming in here and then going here maybe and decreasing. But we know that something happens here in between, whatever, to get it to from here to there with this smooth curve. I'm just making up the middle portion here. So let's put a little box around here. This is just whatever is going on in here. The question is, could this support, the ratio of students to computers going into the 21st century here, or in the 21st century? Then essentially what I'm seeing here is that our ratio of students to computers is going downward. And when we say students to computers, this is kind of like saying I used to have 20 students to one computer, and now maybe I have 10 students to one computer, and then maybe in the next few years you have 5 and then 1. Basically, there are fewer students per computer, meaning there are more computers per student. And so I would say that yes, this is reasonable, just for that reason right there. This is reasonable because the number of students per computer is decreasing, or must be decreasing on the right-hand side, which is a good sign. So that's what we mean by end behavior. We're going to use that going forward to help us graph these polynomial functions. Cheers.